Hello, my name is Justin Hunt, and I work under Dr. Hyunglae Lee at Arizona State University. And I'm here to talk to you about a novel parallel-actuated shoulder exoskeleton that we have developed, and our efforts to optimize its stiffness for a variety of tasks and workspaces. Our research goal for this project was to design an exoskeleton joint with low inertia and high stiffness. In order to do this, we designed a novel parallel-actuated architecture that had these properties. I'm going to play a short video for you that describes how this architecture works. Here you can see a shoulder exoskeleton with a plate that moves about the shoulder joint and is actuated by 3 actuators. Each of these actuators has multiple degrees of freedom that are coupled in order to generate circular motion, as shown here. By adding a revolute joint to the base of each actuator, we can turn that circular motion into spherical motion. The placement of these actuators is flexible, so we can position them anywhere we want, and that is shown here. We developed a prototype of the shoulder exoskeleton and set out to optimize its stiffness through selection of actuator placement locations. In order to do this, we developed an analytical stiffness model and validated that model by coupling the shoulder to a 7-degree of freedom robotic arm and then perturbing the shoulder. We would measure the interaction forces and confirm the results of our model. With the stiffness model validated, we then selected the workspace in which we wanted to search for an optimal solution. On the left here, you can see the solution for a search of the entire workspace. On the right, you can see a search of just the sagittal plane. Now this would be in the case of, say, lifting a box, whereas on the left, you have your solution for an entire workspace and is more generalized. On the top, you can see a cluster of solutions, each centered about a black dot, which represents the mean best solution. In the middle, you can see the actuator placement for that solution. And on the bottom, you can see the translational and rotational stiffness ellipsoids associated with that solution. And with that, I would just like to conclude the talk with a few of our main discussion points, and thank you for your attention.